Chapter 2 exercises section 1. Problem 1. Find the domain and range of the following set of ordered pairs. When a function is defined by a set of ordered pairs, the domain is the first element in each ordered pair. So we can symbolize the domain by the letter D, and in set notation we can write the first element of each ordered pair to be 0 and 10 and 20 and 30 and 40. The range is the second element in each ordered pair. And the range will symbolize that by the letter R, and we'll write the second element of each ordered pair being 9.1, 6.7, 10.7, 13.2, and 21.2. And that would be the domain and the range. Problem 2. Given the following set of ordered pairs, determine whether it defines a function or a relation. To be a function, requirement is that each input has one and only one output value. And in this set of ordered pairs, the input of 5 has two corresponding output values, one being 6 and the other being 8. So this is not a function and is instead a relation. Problem 3. Given an additional set of ordered pairs, does this define a function or a relation? First, check each ordered pair and make sure that the first element is listed only once. 1 goes to the output of 2, 3 goes to 4, 6 goes to 5, and 8 goes to 5. Although the output value of 5 is repeated, each input goes to exactly one output, so this determines a function. Problem 4. Solve the linear equation 2x plus y equals 6 for y, and then determine whether we have a resulting function or a relation. We'll subtract 2x from both sides of the equation to isolate the y by itself, giving us negative 2x plus 6. If this is a function, then each input for x, when multiplied by negative 2 and added to 6, will give us one and only one output value for y, and it does. So this represents a function. Problem 5. Same directions as problem 4. So we'll take the given equation and attempt to isolate the y value. First, we'll subtract x squared from both sides, giving us y equals 1 minus x squared. And then taking the square root of both sides always gives us plus or minus in front of the square root. And that will be a problem because each value of x, when inputted in, will give us two values of y correspondingly. So if x is 0, we'll have an output value of 1. And when x is 0, we'll have an output value of negative 1. And that makes the double valued. So it is not a function. Problem 6. Evaluate the given function for each of the following. To compute f of negative 5, we carefully replace each x by negative 5 using parentheses and do the resulting arithmetic. 25 plus 10 added to 7 will give us an output value of 42. Now we wish to replace each x by the quantity x plus 4. So we'll have x plus 4 in parentheses squared minus 2 times x plus 4, and then add 7. First, we need to square out x plus 4, giving us x squared plus 8x plus 16. Now distribute the negative 2 through the parentheses. Negative 2 times x is negative 2x. Negative 2 times 4 is negative 8, and then add 7. Identify any like terms we have there, and we can write our final result to be x squared plus 6x plus 15. And finally, to compute f of negative x, we simply take each x and replace it by negative x, and then perform the indicated operations. Negative x squared is positive x squared. Negative 2 times negative x is positive 2x, and add 7. Problem number 7. Graph the function f of x equals 2x and g of x equals 2x minus 3 in the same coordinate system. We wish to use values of x that run from negative 2 through positive 2. So to compute the functional values for f, we simply multiply each of the x values by 2, giving us negative 4, negative 2, 0, 2, and 4. To generate the output values for g is the function 2x minus 3. We can simply subtract 3 from each of the x coordinates in this column, and that would be a faster way to compute the values of g. So doing the subtraction there would give us negative 7 and negative 5, negative 3, negative 1, and 1. Now we wish to plot these values in the coordinate system. Negative 2 gives us negative 4, negative 1, negative 2, 0, 0, 1, 2, and 2, 4. And we will draw that function in there, labeling that as f. G, plotting those points, negative 2 gives us negative 7, negative 1 gives us negative 5, 0 gives us negative 3, 1 gives us negative 1, and 4 gives us 1. 2 gives us 1. Draw in that function there, and label that as G. These two graphs have two features in common. One is that they are parallel, and that is because the slope is the same for each of the functions. And the second is we can generate the graph of g by simply subtracting 3 from every y value on the graph of f, and that's called a vertical translation, in this case by 3 units. Problem number 8. Use the vertical line test to determine whether the graph shown represents a function. If we pass any vertical line through the graph, it can only intersect that graph one time. And any vertical line passes through this graph one time. It would not be a function if, say, we had a curve like this that came back upon itself. And if we choose a value of x here, that would generate 2 y values, and that would be an example of not having a function, since each x corresponds to 2 different y values. Problem number 9. Use the graph to determine the value of g of negative 20. You can observe here by looking at the graph, we have a horizontal line for all x less than negative 4. So the function g of x is permanently equal to 2 for all x that are less than or equal to negative 4. So since the value of x we have is negative 20, g of negative 20 will also be 2. Use the same graph to determine what values of x will give g of x equal to a value of negative 1. So g of x equals negative 1 means if the y value is negative 1, find the corresponding x value that makes that happen. So we go to the graph, locate the value of -1, go over to the graph, and then up to the x-axis, and that would be the value of x that we seek. So here, x is equal to 1. G of 1 is -1. The x value is 1. That makes g of x -1. Find the domain and range of the graph shown. The domain is the set of x values for which the function is defined. So we are looking on the left and the right, the extent to which the function is defined, and that would be values of x that are between -2 and 1. There is no point associated at -2, and there is at 1. So we must include the value of 1, but not -2. To find the range, we look at the y values for which the function is defined. And that is the vertical direction here, the extent up and down. And we have y values of -1 up to a value of 2. 2 is not included, -1 is. So all the y values between -1, including -1, up to 2, but not including 2. Problem 12. Is it possible for a function to have more than one y-intercept? Well, assume it does. What would the resulting picture look like? Let's draw something that has at least one y-intercept and make a second y-intercept. And to do that means that x equals 0 will have two y values. And that makes x equals 0 double value. And so no, it is not possible. And that concludes section 2.1 exercises.